Hello, class. This lecture will be on section 3.5, which deals with ideas of graphing. And I'm going to use a lot of the slides to illustrate this. And so the idea of using some algebraic techniques to take a simple graph and kind of make it more complicated and move it around up and down, reflections, compression, contractions, etc. As I said, it's a little bit archaic in these days, where most people would just take the whole equation and go on Desmos and type it in and see what the graph looks like and not have to do these types of things. It was much more useful for me than it was for you when I was taking college algebra, because we didn't have the cool technology. But these concepts are still important. So what I'm going to do is walk through these concepts with you. And the first one, and I think the easiest one, is the vertical and horizontal shifts. So the vertical shift, remember, vertical is on the y-axis, right? So when we talk about a vertical shift, if we look at a vertical shift, we go up or down. That's what we mean by vertical shift. And the definition that we're going to introduce for that is right here. So if you have a function or an equation and you add a value to it, in this case, it says k. If k is positive, the graph moves up k units, and if k is negative, the graph moves down k units. And so to give you an example, let's take a look at this equation. If you did f of x equals x squared, and we want to add 3 to it, what would happen to it? Well, you would take the equation, take the graph, which is black here. And I believe in your homework, they'll give you the original graph and then ask you to move things around depending on what they do to the equation. And so here we add up 3, and you can see we move up 3. The way I like to think about it is you want to take one point and see what happens. And usually taking the origin is the best point, right? So here's what I mean by that. So we have y equals x squared, and then we had y equals x squared plus 3. So, and this would be y1, and then this would be y2. So what happens? Well, if we plug in x equals 0 to the first equation, y1 equals 0. And if we plug x into the second equation, what would y2 equal? That would be 3. So you could see what we're doing is we're just moving that point up 3. And if you move one point, all the points are going to end up moving the same way. So what's really nice about, I think the book does a good job with this. So read this section if you're struggling with this a little bit. But it's nice to make this little matrix too. You see this table 7 here? And so it gives you the ability to see what happens to the y values when the x's move around. And so that's the vertical shift. If you went down, for example, in this case, if we subtract 4, basically instead, now we're going down 4. And so the y is nice. It kind of makes sense. The vertical, excuse me. The horizontal is a little bit trickier, because if we talk about a horizontal shift, there we go, is that now instead of moving the y's, we're moving the x's, right? Because when we do horizontal, now we're going this way, right? Either going to the right or to the left. And what's weird about that is that now we want to affect the x variable, not the y. And so it's opposite. If you subtract, you move to the right, and if you add, you move to the left. And that's a little bit tricky because it's counterintuitive. But if you think about what the how things work at the origin, it might help you a little bit. And so, let me clear this up. Let's take a look at a couple examples, and I'll show you what I mean. So if we take a look at this equation here, and this equation is g of x is x minus 2. And the original equation is, let's say, f of x equals the square root of x. So what we want to do in this case is f of x is the square root of x, and g of x is square root of x minus 2. So this one's a little trickier, so I'm going to try to do it here, but I'm not a very good drawer. But what you start with is they'll give you this, and this is f of x. So at x equals 0, y equals 0, and it kind of goes that way. So this is f of x. So if you think about the origin, right, and this is 0 here, and when you plug in 0, y equals 0. But what happens in the g equation? What happens if I plug in g of 0? What do I get? Well, you can't plug that in, right? See what happens? 0 minus 2. You get square root of minus 2. So you have to realize that some of these numbers just won't work. So the question is, what value of x do you plug into g of x to get the y value to be 0? And that would be the number 2, right? You plug 2 in, you get square root of 2 minus 2, and that would be square root of 0, and that equals 0. So you see that when we graph the g of x, when x equals 2, y equals 0, that would be this point here. And so when you graph this, it would look like that, right? So it's just, this would be g of x. So that's what we mean that when you subtract from the x variable, you actually shift to the right. And if you look at the pre-graph, let me show you. Here's what the book's graph looks like. And so again, think about where the origin or where the start of the graph is. It really helps me. Here's another example that instead of subtracting 2, we're adding 4, right? Square root of x, and g of x is square root of x plus 4. So when we do that, the 0 point now is minus 4 plus 4 gives us 0. So you see we move 4 units to the left. So again, the black is square root of x, and the blue in this case is square root of x plus 4. So the next thing we'll talk about is this idea of compression and stretches. I don't use this, again, very much anymore, because I'll just graph it using technology. But the definition of the compression and stretching is you're taking a graph or function in this case, and you're multiplying it by a number a. So you see here that we have y equals a times f of x inside this equation. And so if a is bigger than 1, then what you're doing with regards to that, you're going to be stretching it. And if the a is between 0 and 1, then you're going to be compressing it. And we'll talk about what happens to the graph when a is negative. That's a different discussion. But here a will always be a positive number. It has to be greater than 0, because if you multiply by 0, it just goes away. So if we take a look at our square root function again, and say like we look at square root, and then take the square root and multiply it by 2. So basically that's going to be a vertical stretch. And you'll see that if you look again, the black is the original, y equals square root of x. And you can see that the blue over here is, oops, the stretch. And you can see that basically you're stretching it and everything is kind of doubled, right? So it's going to be bigger in that aspect of it. And so here's an example of compression. So now what are we doing? We're making it smaller. So we're going to multiply it by a number between 0 and 1. In this case, 1/2. And so when you do that, the black is the graph of absolute value of x. And you can see the blue is half that. And what's really nice, it's okay to make a little chart. And like I said, usually you just plug it into equation or the Desmos program and you see what it turns out anyways. But back in the day, to make a little chart was quite helpful as well. So I'm going to stop this and we're going to finish this on another recorded lecture. So this is the first part of section 3.5.